Okay, thank you very much for the organizers for putting together this Nottingham node of the international series of meetings. And thanks for inviting me to open with some introductory remarks, as I understand them, to the type of theory research on relativistic quantum information and related topics that we do here at the University of Nottingham. So I should come clean and say that my background is solidly in theory, curved space-time quantum fields, to some extent quantum gravity, and that is what I will be mostly addressing here. But over the past 10-15 years, I have become convinced that this is an area that has solid experimental connections. This is a topic that can be pursued in collaboration with experimentalists, and that collaboration between theory and experiment is very much the overall tone of all of today's talks. Plan. So I'd first like to tell a little bit about the relativistic quantum and information research that we do here at the University of Nottingham. And then I'll tell at a general level about the Unruh effect, the effect that is a paradigm of the things that we'd like to analyze, what we'd like to measure, and related phenomena, and where we are from the 70s, totally theory, to the present, where we have an interplay of theory and experiment. Let's start with a question. I understand that the local crowd is a Nottingham crowd, okay? And the real-time interaction with the international audience doesn't quite work. So in some sense, this is a thought experiment version of a quiz. But suppose you were asked, name a famous person from Nottingham. Right, I have a pretty good guess as to what the first name is that comes to your mind. But I'm not heading that direction here. So I should like to think of a person that is demonstrably a non-fictional person. And in case you think of the Sheriff of Nottingham next, no, I don't want to go that direction either. I want to think of a Nottingham person with a clear mathematical physics connection. In fact, so clear a connection that all of you, whether in this room or everywhere listening, have probably used the work of this person. Maybe studied it, maybe have taught it.
You.
Well, I'm thinking of a different order of magnitude, both in time and space and in space-time, right? So we can't really do this interactively. So I'll put up a picture first. So we are talking about early 1800s. We are talking about a Nottingham miller called George Green. There is his windmill. It still stands. It's been restored. It's a working windmill. You can go there, you can visit, you can go up there, you can, in the shop, you can buy flour that has been ground there in George Green's windmill. Okay? And the name, it's a fairly common name, so as such, it might not ring a bell, but the mathematical physics connection is, this is the Green of Green's functions that we know, love, and use. Okay? Green was a miller by professional. As a mathematician, he started entirely self-taught. He had about 1 year of formal schooling. And then, when the wind wasn't blowing, he taught himself mathematics, continental mathematics, which was a novelty at that time in UK. And he wrote an essay, right, mathematical analysis to the theories of electricity and magnetism. This is where he came up with the idea of Green's functions. He also came up with the idea of potential, as in electric potential and so on, in this essay. He published it by crowdfunding, he went to his friends and he said, okay, if you promise to pay me this much, you can get a printed copy of this essay that I'm writing here. Okay, and he got published. And this is where Green's functions came from. Later, he got some formal education in mathematics. He went to Cambridge, did a degree there, became a college fellow, wrote half a dozen papers. One of those papers is actually quite relevant for today. One of his papers is about water waves in a canal. That's closely related to the kind of research that we do here in Nottingham. And in that water wave papers, Green introduces something that we would nowadays recognize as a precursor of the WKB or JWKB approximation in quantum mechanics. So we have solid traditions in mathematical physics of the kind that we are doing in Nottingham, going back to some 200 years. The University of Nottingham cannot take credit for Green. The university started some decades after Green had passed away. But the university is here. It is a major research university. And so we do relativity quantum information. We do relativistic quantum information. And as things often are at British universities, these topics are split between physics and mathematics. Some of it is done in mathematics, some of it is done in physics. So, and I've illustrated the split over here. So we've got a School of Mathematical Sciences where we have, first of all, we have the gravity laboratory, Silke Weinfurtner's gravity laboratory, that is at this forefront of the interface of theory and experiments on analog spacetime. Then we have a gravity group. We have a quantum information group. It's quite a lively group. They tend to do mainly things that are not particularly relativistic, but there is lively interaction going on there. There's also some quantum gravity type quantum mathematics, and there are interactions over there. So that's on the mathematics side. And then in the School of Physics and Astronomy, there's basically theory and experiment of solid state of various kinds and known by keywords put over there. And then there's a particle cosmology group. And so we are quite a lively bunch with lots of connections. Right, and it looks like we might be split. Not really. I mean, we have organized ourselves into the gravity-oriented things. We have organized ourselves into the Nottingham Center of Gravity. Okay, I did not come up with that title, but that's what we are called, Nottingham Center of Gravity. And right, so it includes people from all of this, and so that's the overarching way how we are organized. And I could not resist putting up here a photo. So this is at the Nottingham Center of Gravity web pages. So the big part, it's a genuine photo from about now, some contemporary photo. It's the main administrative building of the University of Nottingham main campus here. And in the inset, you have a photo from 1930 taken at the very same location, and that is from a visit of Einstein to the University of Nottingham. In fact, we still have the blackboard that Einstein used for his talk. It's preserved. It's in one of our meeting rooms. If you Google up the Einstein blackboard, there are exactly two hits that come up. One is at Oxford, in Oxford at the Museum of Science there, and the other one is here at Nottingham. We think ours is the better one, okay. So we do research relevant for the topics of this series of meetings. What I'd like to do next is, I'd like to look at the motivating theory behind the type of research that we do. So the general theme is really modeling quantum fields, relativistic quantum fields in the laboratory and the theory supporting it. But if I were to start from a key concept that underlies our thinking, the key concept would be the Unruh effect. Okay, so this is a prediction from the 1970s. prediction in relativistic quantum field theory that says if you take the Minkowski vacuum, the no particle state, the traditional no particle state in Minkowski space, and then you, as an observer, you accelerate through it uniformly, linearly, with constant acceleration, then that vacuum doesn't look like a no particle state to you anymore. Instead, it looks like a thermal state. You react to that state as if it was a thermal state in a temperature that is proportional to the seat of Pan's acceleration that you feel. There's the acceleration and there's the numerical constant. So this is a prediction. It's a prediction from the 70s. Was a surprise when it came, okay? But the input, it's entirely standard quantum field theory. There's nothing exotic in the input. There are some approximations, like you need to wait for a certain amount of time and the coupling needs to be sufficiently weak and so on. But this is an entirely standard prediction of standard quantum field theory. And this isn't just some equations that you put on a piece of paper. This is a prediction on which you can imagine a Gedanken experiment, a Gedanken test. So my favorite way to think of it is in terms of excitation and de-excitation probabilities of some system you have. So suppose I am in my spaceship, accelerating linearly. I can feel like I'm using my rocket engines, and on the shelf of the spaceship I have jars of different types of atoms, like this: antimony, arsenic, aluminum, selenium, and so on. And once in a while I look in each of those jars and I check what fraction of those atoms is in their ground state, what fraction are in their excited state, and I see that it's different from jar to jar, and in particular I'll see that it's different from what I'd have if I wasn't accelerating at all. This is what the Unruh effect predicts. It says, well, that the downward probability transition and the upward probability transition, they are related by the exponential law. We know it as the detailed balance law, where the gap, the transition gap between the ground state and the excited state is over there, and there is the temperature now being proportional to the acceleration. So this is something that you, in your spaceship, accelerating, you could go and imagine testing it. So you could say it's so real an effect that you can cook your steak with it, given sufficient acceleration. However, to date, no steaks have been cooked with this phenomenon. And the thing has, why? It has to do with the numbers over here. You see that the dimensions here, they don't quite match. There are some constants of nature missing. If I put the constants of nature in, right, no steaks cooked, because there's a small number in everyday units upstairs, there's a large number speed of light in vacuum downstairs, and so to get to 1 Kelvin you'd need to tend to 20 meters per second squared. So there's no direct experimental test of this prediction. It's a standard kind of prediction, but there's no observation. So that's the showcase example. There is a larger context here. I mean, this is standard Minkowski quantum field theory. The history didn't come from thinking of Minkowski quantum field theory. The history came from thinking of what's happening in curved space-time. Okay, and that's very much the formalism by which this prediction is found. And so the bigger context is you have a local quantum system, like your jar of antimony atoms or something, interacting with a quantum field. And usually here you are interested in a quantum field that's spread all over space-time. It's not like a typical quantum optics scenario where you say you have a focused laser here and you're interested in what the laser does. You are here interested in a quantum field in a state that's spread all over, like the vacuum, could be a thermal state, could be something else, but a very non-localized state. And that's the bigger context of here. So what happens in this sort of interactions with a local quantum system and a field that's spread all over? if we go really historical, I mean, that there is such an interaction. It's been known for, I don't know, since 40s and so on. I mean, if you think how the fluorescent tubes in this room works, there's light that comes from here. You excite the atoms there by electricity, and then there's a spontaneous decay to a lower energy state. How does that spontaneous decay come about? It comes by interaction with the vacuum of the quantum electromagnetic field. This is not something you can tell a second-year undergraduate student, right? But it's quantum field that causes the downward transitions over there. Here we are thinking of this phenomena in the larger setting of non-trivial motion, possibly some non-trivial spread out states, and we could think of time-dependent situations. One of my favorite examples is a local observer falling into a black hole that Hawking radiates. What does that local observer see when they are still far from the hole, when they get closer to the hole? Maybe when they get in the hole and have crossed the horizon. And I am reminded that in last week's session, Rob Mann talked about research in that specific problem. So this is the larger context. I'm going to be qualitative here, and so these are the only equations that I'm going to show. But I'd like to next list what kind of problems this setting creates, what kind of problems you need to start thinking about. And still on the theory side, so facets of theory, if you like. So first there's this notion of a local quantum system. What do you mean by this local? I mean, so you might think like there's an atom, okay, and it's localized in certain sense, but atoms are complicated things. There's, I don't know, spin-orbit coupling, and they are different types of orbitals. They are messy things. So how would you sort of model a local quantum system? Your first thought might be, let's go point-like. Get away all with those finite size complications and so on. Now, this might give you pause, because when you start studying quantum field theory, one of the early things you learn is that if you ask things about a space-time point, you can expect that things are going to turn singular. So you might feel uncomfortable about this. Now, if you say spatially point-like, so you still have a time dimension in which you go through the space-time. There you have some more hope. Okay? But it's a non-trivial question. Does this make sense? It works more often than one might expect. I mean, so this goes back to DeWitt's observation in the 70s. So you often work in perturbation theory, and often if you work in low-order perturbation theory, the point-like system, it works way better than you might think. And in low space-time dimensions, it works particularly well. But ultimately, it does produce singularities for you. It tells you that you are trying to do an idealization too fast. For example, if you ask about the experiences of a single atom, you're fine. But if you start asking about entanglement between two atoms moving in different places in this language, then the point-like character, it starts to create a problem for you. So that's something you need to think about. If not point-like, then what? I mean, some sort of confining potential, maybe. Maybe something like a two-state system with a spatial profile. So how does that work? Well, there's a lot of work on that topic. And so if you ask simple enough questions, it works beautifully. And there's a vast literature going on it. But I would argue, if you start asking questions that are too delicate about how things are localized in space-time, you'll find that these profile systems, spatial profile systems, they tend to violate relativistic causality. And this is an observation that goes back to Sorkin in the 90s and has been developed much since. So for some observations, it's fine. Ultimately, of course, you'd like to use relativistic fields. We think that the space-time, our fields that live in a relativistic space-time, they are relativistic fields. They are hard to localize. I mean, you can sort of localize the photon here, but then it keeps spreading when it goes. So they are hard to localize. You might try to localize them with a cavity, and there is literature on this. So you postulate that you've got a cavity that's totally confining, maybe even partially confining, and then you let it move in space-time. There's literature on that, but you need to then start thinking what is the sense of localizing one field and maybe not localize other fields. And also you need to think about what do you mean by rigid cavity. This is the rigid body problem in relativity. It doesn't really exist except in certain special cases. So these are facets of the theory you'd need to think about. I've got a second overhead about these facets of theory. Another thing you need to worry about, how do you do the coupling between your local system and your spread out field? A lot of the literature goes perturbatively small. You do perturbation theory in a coupling constant. Okay, and that's certainly a good place to start. We love doing perturbation theory, don't we? Right? And yes, at least in theory, right? It works, right? It has some issues. In particular, if you wanted to consider the long time limit, you can see there's an intrinsic contradiction. If you want your interaction to be weak so that perturbative treatment is valid, but you want your time to be long so that there's lots of time to interact. I mean, there's a problem of internal consistency. You need to address this somehow. And I think for the purposes of today, let me leave it at that. You could talk about a simultaneous regime of large time and small coupling and so on. But there are significant technological things that you need to worry about here. You could try going non-perturbative. That's, of course, much more difficult. On the sort of mathematical side, theory side, there is some work in that direction. I've mentioned a few things here. They tend to be existence type analytic work, and they are good. So there are sort of mathematics type, existence type results, and then the challenge is how would you convince an experimentalist that an existence type result is something they should be worried about, or they should pay attention to, but it can be done. Then there's numerical work, that's quite common. For example, there's an early paper by Hu and Lin where they look at the Unruh effect in a genuinely non-perturbative regime. And they find some regimes where the Unruh effect is a transient effect and goes away if you follow the system fast enough. But so this non-perturbative thing, it's another facet you need to think about. And finally, right, you need to think about this time dependence. So you might be interested in something that's stationary, but then you need to worry how do you start the interaction, how you do end this interaction. Or you might consider a genuinely time-dependent situation, like this observer falling in the black hole. That is a genuinely time-dependent situation, and then you need to worry how you characterize this genuine time dependence versus any switch on and switch off type phenomena that you've introduced when doing this. So there are some theory issues you need to consider here. Toward experiment, right. So we are talking here about the analog space-time program that says there are laboratory systems in which you have excitations obeying a relativistic wave equation. The seminal paper here was Bill Unruh's paper from 1981. That was in the water waves context. Then there's Bose-Einstein condensate, there's helium, and so on. And we know that well, so if there's a relativistic wave equation here, same equations have same solutions as Bill Unruh has been repeatedly advocating. So what can you test a relativistic system by these systems that have a non-relativistic fundamental physics, arguably, but an effectively relativistic field equation. And that's the that's really the interface that we are interested in. And the specific problem that I'll mention here is the Unruh effect, but in circular acceleration in this analog space-time context. Now, how should I think of the time budget? Okay, thank you. So, right. So, we'd like to think of the circular motion. We'd like to probe the the Unruh effect in this context. Water waves. Well, water waves are pretty classical. The Unruh effect is supposed to be a quantum effect. You can test some of the underlying classical dispersion things with water waves, but you wouldn't expect to test the genuine quantum regime with water waves. But we have Bose-Einstein condensates, we have helium surface waves, and in those systems we have a genuinely quantum system, and there you have an effective relativistic field equations. Those are a good arena for looking at the Unruh effect. So Bose-Einstein condensate, helium, they are good things. And why do we think this is better than the space-time setting with my spaceship and the jars on the shelf? Remember the formula, one of the two formulas that I showed. What was the formula for the Unruh temperature? It had the speed of excitation, speed of light there in the denominator. And that was one of the reasons why in the space-time setting Unruh effect is difficult to observe. But if you go to one of these systems, the effective excitations, they don't go at the speed of light in vacuum. They go at a speed much less. And that makes the effective Unruh temperature higher. It's something you can, it's something that's more easily experimentally accessible. So good systems. Circular motion, why? Well, if you try to do linear motion in a lab, you will eventually run out of your lab. I mean, given a lab with normal size budgets. But if you use circular acceleration, you can run your experiment in a circular motion, in theory, an arbitrary length of time. Okay, so that's a good selling point for circular motion. Another circular motion has to do with the technical aspects of how time dilation occurs in the theory of the Unruh effect. For the purposes of today, let me just say that if you are working with this circular motion, those time dilation things, they are entirely straightforward. You don't need to ask your engineer to do something with your Bose-Einstein condensate or your helium to put it there. These time dilation things, they are entirely at the end at the data analysis. So this is a nice setting. Now circular motion, it's not linear motion. So the Unruh effect there, it's not quite the same as the detailed balance formula that I showed. But right, long story going back to the 80s and so on. But the bottom line for here is it's almost like it. There's some additional dependence on parameters, but for the purposes of detecting something, there's something to detect, and it's basically the same thing. And finally, so remember we wanted to have some material local system going around, in this case going around in circle. If you are using these Bose-Einstein condensate or helium, you can simplify things, and instead of putting a matter system there in your field, in your effective quantum field, you can collect and sample those fluctuations, those quantum fluctuations, vacuum fluctuations by a passing laser beam, and then do data analysis on them later, and we'll have talks, we'll have that discussed in later talks today. And on that note, I think I would like to end this interview. So over the past years, I have become convinced that the analog space-time paradigm, analog space-time system, it is a viable place to look for, to test experimentally predictions of relativistic quantum fields, and in particular this question of how a local matter system interacts with a spread out quantum field. And it's at that interface that we are working here. And we take PhD students, we host postdocs, sometimes we have internally funded postdocs, sometimes we host postdoc applications to research councils, do get in touch with us. And on that note, I'd like to end here.
Thank you, Jorma, for the very comprehensive overview of everything we're doing theory-wise at the moment. I'd like to open it up to any questions, both online or from the room itself. So if anyone has any questions first from the room. Yes, Vito.
Jorma, in your opinion, what are the challenges for us when doing the experiments to try and measure the analog number effect? What do you think are the main things we should be careful about, other than the experimental technicalities?
I think we'll have a talk about data analysis later today. That is something I would dearly like to understand better. On the theory side, that I would see that as a sort of major things where things need to be cleared up.
Okay. Are there any other questions in the room? Are there any questions online? Okay, well, if not, then thank you very much again. If you'd like to thank you again for speaking, and